everyone, welcome to our lecture in fundamental of casting and solidification. So, today is the fifth lecture on pattern allowance 2. In last lecture we have discussed about pattern allowance, where we have started shrinkage allowance and we have understand why we need shrinkage allowance. There are three kind of shrinkage allowances: liquid to liquid shrinkage due to volume changes, density changes, so volume changes during the cooling, or obviously you are doing melting or something, heating will be also inversely. Okay. Then liquid to liquid shrinkage, liquid to solid shrinkage, and solid to solid shrinkage happens, and liquid to liquid and liquid to solid shrinkage is taken care by riser, whereas solid to solid shrinkage care by the pattern design. We have solved one numerical problems also, where external features has added the volume. Okay. We have to add the volume. Finally, you have to increase your volume because you have to shrink, you have to compensate shrinkage. So, if external surface, your dimension will increase, internal surface dimension will decrease. So, overall volume will be going to increase. So, these are the standard data I have shown in last class. Now, if you are going to make metallic pattern, okay, so double shrinkage comes, double shrinkage allowances. What that means? If you want to make metallic master alloy pattern, okay. So, that time we say double shrinkage allowance is to be provided on the pattern dimension if it is used for the casting the metallic patterns, which would be ultimately used for the molding to make care of shrinkage of actual cast metal as well as the shrinkage of the pattern metal. Okay. There is two shrinkage. First, I have to give shrinkage. First, we have to give shrinkage for the first material. Okay, what we have to cast, and on this shrinkage we have to give the master pattern. There are two metallic system involved. So, it need two shrinkage, and you can solve these problems by adding both, or you separately also you can do. So, you will see a numerical problem and then you can understand. For the same example as shown in previous lecture, if the master pattern is to be made of aluminum, we want to make a master pattern which is made of aluminum, then calculate the dimension of wooden pattern. Okay. Then calculate the dimension of wooden pattern. I have to make a wooden pattern first, then final objective is to make aluminum pattern, which is used to be for making the aluminum pattern for casting of plain carbon steel. I have to do casting of plain carbon steel. Our objective is to do cast plain carbon steel, first step. Second, what is objective? I have to make a metallic pattern also. So, initial pattern will be wooden, then I will add plain carbon steel shrinkage. For the aluminum pattern, I will add aluminum shrinkage as well. So, double shrinkage allowance will be added to for this problem. Okay. So, in this case, this problem is given plain carbon steel shrinkage allowance is 21 mm per meter if length is less than 600 mm. So, all dimension like 80, 150, 200, 100 all are less than 600 mm. So, one data is enough. Similarly, aluminum shrinkage allowance for any dimension is 13 mm per meter. Based on that, we will solve this numerical problem. So, for plain carbon steel wooden pattern, okay, for 200 mm allowance, 200 into 21 by 1000, 21 mm. Okay. So, what is the value? 4.2 mm. So, 200 mm will be 200 plus 4.2, 204.2 mm dimension. Initial dimension will be 204.2. Similarly, for 150 mm allowances will be 150 into 21 by 1000, 3.2 mm. So, what will happen? So, 150 mm convert will be 150 plus 3.2 equal to 153.2 mm. For 100 mm allowance equal to 100 into 21 by 1000, 2.1 mm. So, 100 mm will convert 100 plus 2.1, 102.1 mm. Okay. For 80 mm, 80 into 21 by 1000, 1.7 mm. So, what is the value? So, 80 will convert into 80 minus 1.7 equal to 78.3 mm. For the first shrinkage, these are the values. Okay. For next shrinkage, for metallic pattern design and for 200 mm allowance, for 200 case the allowance will be 204 already there. So, I am just calculating allowance. So, I will just remove this. Okay. 204.2 into 13 by 1000. Okay. And so, 200 mm will convert 204.2 plus 204.2 into 13 by 1000 and answer will be 206.85 mm. Okay. For 100 mm allowance 102.1 into 13 by 1000. Okay. So, 100 will allowance will be 102.1 plus 102.1 into 13 divided by 1000 and the value will be 103.43 mm. For 150 mm will be 153.2 into 13 by 1000. So, 150 mm will convert into 153.2 plus 153.2 into 13 divided by 1000 and value will be 155.20 mm. For 80 mm allowance will be 78.3 into 38 by 13 by 1000. So, 80 mm will convert 80 minus, sorry, not 80, it will be 78.3 minus 78.3 into 13 by 1000, and answer will be 77.28 mm. So, we will sketch that. Okay. The okay, it was 200 mm, this was 100 mm, this was 150 mm, this was 5 was 80 mm. Now, new dimension will be, your dimension will be bigger, you can take okay, and diameter will be, and new dimension will be 155.2, 103.43, and 200 will convert into 206.85, and phi will be, new phi will be 77.28. All are in mm. Okay. Something like this dimension will observe for the double shrinkage when we are going to make a pattern of aluminum for the casting of plain carbon steel. Okay. Now, after the addition of shrinkage allowance, now what will happen? We casting will do casting, contraction will happen, and due to contraction we are already added a shrinkage allowance. Now, there is sand around that, okay. There will be grains, will fine, it will not too much fine and all. So, there will rough surfaces can generate, okay. So, there is chances that you have to machining needed. It not necessary always, it's depend with lots of factors, but if you need some clean surfaces, then you have to add some, you have to remove the unwanted materials, uneven surfaces. Now, let us assume you have made 10 cm, you want 10 cm product, and after the shrinkage allowance you are getting 10. Now, surface is not smooth, then what you will do? You machine something. So, what will dimension? Obviously, lower than 10, then you will not, customer will not accept, then what will happen? So, for that purpose we add some additional allowances, that is called machining allowances. Machining and or finishing allowance is extra material added to the casting to enable their finishing or machining to required size. Okay. We give some finishing allowances or machining allowance, some people say finishing allowances also. The type of machining allowance provide would depend metal cast, which metal you are going to cast, type of molding used, which type of sand and which method you are using, like investment casting, because pattern are made of wax, they are very smooth, they called accuracy is very high. So, they not too much need machining in that case. So, which kind of molding process you are using, class of accuracy required on the surface. Let us assume I am just going to make a chair, does not need too much surface finish, high extent surface finishing, but I want to make turbine blades, there need lots of finished surfaces. So, how, where you need machining allowances will be more, depends on the which kind accuracy you want, and then complexity of surfaces. Okay. All things vary our machining allowances. Okay. One way of reducing the machining allowance is to keep the entire casting in the drag mold. Okay. To reduce machining allowance, to avoid, to reduce, not avoid, to reduce machining allowance, you can keep your whole pattern in one piece pattern into drag mold, so that dimensional variation and other defects due to the parting plane are reduced to a minimum. at the parting plane the misalignment can happen. Okay. So, try to do, but it is not very feasible, because our shape is not going to be very simple always, and one single piece pattern is very difficult to make. So, it is a very less chance to do. Okay. But if you have only single pattern, try to keep into drag. So, mismatch kind of concept and these things become minimum. So, based on the foundry practice, these are the dimensions and material based things like cast steel, steel based materials, ferrous alloy, the dimension, if your dimension is less than 150 mm, then if you are making hole, then machining allowance will be 3 mm. Surface allowance on any surface 3 mm, on cope side it will be 6 mm. So, what does mean cope side? This is mold, cope and drag. Let us assume this is your actual pattern and mold cavity. If you are like this, then machining allowance is higher in this case. This is the actual one. This is 6 mm. Okay. This is 3 mm if your dimension is less than 150 mm. So, machining, where you will add machining allowances? Obviously, because you have to remove the material. So, machining allowance is also a positive addition to a material, but where? In shrinkage allowance, volume should be increased to maintain the contraction, but in machining, where you need a finishing finished surface, you have to add your machining allowance. Simple, very clean and simple. Which surface you want to remove the make a finishing, you have to going to machine, you are going to machining, you have to remove, you have to add the machining allowances. Okay. Similarly, if you are non-ferrous, the length is the machining allowance is less. Okay. Interestingly, if you can see, cast steel has higher surface allowance, machining allowance compared to non-ferrous alloys. Okay. So, we will solve a numerical problem based on that. In previous question, that what will happen, what will the pattern dimension if the surface of casting need to be machined if machining allowance is 3 mm. Since if some problem you are doing a numerical problem and solving that, and chart is given, then you have to follow chart. Okay. This data, bore dimension, surface dimension and cope side dimension for the machining allowance. Problem is directly saying if machining allowance only 3 mm for each any surface. So, you do not have to think too much that data, you have to follow this numerical problem accordingly to given chart. Okay. So, first you have to decide where you are going to keep this, in cope and drag or parting plane kind of thing. So, I am assuming that this is my mold and this is my parting plane and this is my initial design 200 mm, this is height is 100 mm and internal diameter is something like 80 mm. Okay. Based on that, I have to, this idea I am keeping in mind, and I am based on that I am creating machining allowances. So, machining allowance for any surface equal to 3 mm. Okay. So, I have to machine which side. So, I have to machine in for 200 mm, I have to machine this side, I have to machine this side also. So, what will happen? 200 plus 3 plus 3. So, 200 mm surface, 200 mm scale after allowance, after machining allowance. I am not taking shrinkage allowance here. If you are added last problem shrinkage, first add shrinkage allowance, then add machining allowance. So, dimension will be 204 point something plus 6 mm. Two zero 6 mm. Machining allowance 400 mm. For 100 mm, I have to machine here. This is 100 mm. I want machining in this side also. So, 3 mm here, 3 mm here, total 6 mm for 100 mm scale after machining allowance 100 plus 3 plus 3. So, 106 mm. Let us assume it is not mentioned in problem 3 mm and given the chart, what will the answer? So, less than 100 mm. So, surface will be 3 mm and cope side, because I am designing here is a cope side. So, what will happen? 109 mm. Okay. But in problem it is given 3 mm for any surface. So, it will be 106 mm. Now, for 150 mm scale after machining allowance. So, 150 mm, and someone is saying I do not want to machine left side. Let us first we will see 3 mm this side, 3 mm this side. So, 150 plus 3 plus 3, 156 mm. Okay. Okay. Now, someone is saying I do not want to machine in one side, I just want machining in another side. So, answer will be 153, okay, not 156. Okay. Depending on the situation, what customer want, depending on that you can change your scale. For 80 mm scale after machining allowance. Again, what is happening with this? This is 80. Now, we will do boring. Okay. So, what will happen? Here 3 mm, 3 mm, total 180 minus 2 into 3, 6 mm you have to reduce, that will be 74 mm. So, final dimension will be okay. So, 206, 156, 106 and 74 mm as phi. Okay. This is the final dimension for the machining allowance. In draft allowance, third allowance is draft allowance. In this, what we do, if let us assume you are there is a same pattern, okay, there is sand and there is a, I am just taking drag mold, okay, and there is a pattern. Okay. I want to, after ramming, okay, of sand, I want to remove this. So, what will happen? It is, if you remove, the chances there some breakage happen, okay, sand maybe ruptures. Okay. So, what is thing we can do? One way, we can first left, right, front and back, something we will check that. So, it will create some space, something like this, is not it? Similarly, for front and back, and you can easily remove. So, better to give this allowance to the material to remove easily. So, this is the draft allowance. So, at the time of withdrawing the pattern from the sand mold, the vertical face of the pattern are in continual contact with the sand, which may damage the mold cavity. The taper provided by the pattern maker on the vertical surface, so the pattern it can be removed from the sand without the tearing away the side of the molds and without excessive wrapping by the molder. So, you can see what happens. This is the setup, this is solid body, this is the hollow body. So, this is a sand. I am creating hollow cylinder or hollow cuboid kind of thing. This is hollow. So, you can see this taper or draft allowance has been provided to avoid such when removal of the pattern any damage to the mold. Okay. And this is parting plane, this draft allowance, it depends on the parting plane. Okay. The amount depends on the length of vertical side, of the pattern to be extracted from the cope side or drag side, how depth either in cope or drag. The intricacy of the pattern, second dependency on the intricacy of the pattern, method of molding and pattern material. And also we can see the data also suggest that as pattern maker had workshop, foundry man have done practice and done lots of data, and based on that they have got that external draft, external tapering is always lower than or equal to the internal draft. External draft should be always lower or equal to the internal draft angle. So, if wooden pattern you are using, this different depth is there, how much depth you are discussing, okay, below the parting line or above the parting line in the cope and drag. Based on that the contact the angles is given in degree. Okay. So, tan you can theta equal to L by R, you can tan theta you can calculate, okay, and you can multiply the height, and that is the your sorry I am making. So, let us assume this is your, okay, and you have to provide a draft of theta and you want to calculate x, you know h, tan theta equal to x by h, x equal to h tan theta, is not it? You know the theta, angle is already given, you know the depth, okay, how much which depth you are to discuss, okay, and you can give this allowances like. So, what will happen, it is a, let us assume 200 mm, bottom will be 200, top will be 200 plus x, similarly for here x plus x, 2x. Similarly for front and back side also, like 100 mm, 100 mm, okay, like h is 100 mm here, okay, x you can calculate in x direction, front and back and left and right also. So, next is wrapping allowances and sec allowances. Okay. So, it is a value decided by the experience or trial, no guidance can be made for this allowances. When the large any your pattern is to be wrapped for the easy removal, the body cavity gets slightly larger in size. This also cause the increase in casting, size of casting. Okay. To compensate this growth or this increment, the pattern should be initially be made slightly smaller than the required size, because you are doing some ramping and all. So, what happens, size become larger. In a small and medium size casting, this allowance may be ignored, but the allowance should be considered for the large casting or very high precision cases. If you are a small casting and not too much precise casting, you can avoid this. If your casting is large, then you can't avoid, because lots of machining you have to do, lots of cost involvement happens. Okay. So, next is distortion allowance. If thin section you are doing like I section casting, due to residual stresses, it start to bend either this direction or upward direction. So, what they do, casting, this is you want, what happen with that, and so for that if something is I want to make this parallel U, okay. But what happens is going after casting like this due to residual stresses. So, what can we do? We can do some inclination. So, what will happen due to this convert into a state what you want. Sometimes casting gets distorted during the cooling due to typical shape because of residual stresses. This allowance is considered only for casting to tend to get distorted and have irregular shapes. Okay. Left side is showing required shape of a casting, center is showing casting with distortion method, this is showing modified pattern. So, it is a practice, okay. It is not given any numerical value, but it is come with practice, the foundry men practice, and they give the suggestion based on their experiences. Thank you.